In this video, we're going to talk about centripetal force. This may be a concept you've heard of before. In order to understand it, let's first consider projectile motion. We've got an arrow flying through the air here before it sticks into the ground on the other side. What does this motion look like? Well, if we remember when we investigated projectile motion, we could really break it up into two dimensions. We have the x plane, and then we have the y plane. And in the x-plane, that arrow has a clean, straight line for its change in position, and it has a constant velocity. Its velocity is constant because the slope of its change in position is constant, which means that its acceleration is 0. Where in the y-plane, over time, we are going to make a parabola. We're going to start at a certain height, we're going to go up, and then we're going to turn around and come back. And we can see this in our velocity by going, hey, we started at this certain velocity going in the upwards direction, but then we steadily dropped in velocity until we hit our 0 line. We'll call this dotted line our 0 line. And when we crossed that, then we started going in the opposite direction until we hit back on the ground. And so we had a constant, and we'll make a 0 line here. That's 0. We had a constant negative acceleration for that motion. So if I have some kind of curved motion, what are going to be the components of that? Well, we can see from projectile motion that first I need a velocity. I need a velocity that is constant. And then I need an acceleration that is also constant. So I need one plane of acceleration and one plane of velocity without acceleration. If I had both planes having velocity, well, I would end up with a straight line. And so I'd just be moving at the same speed in two different planes. If I had acceleration in both planes, I would also end up moving in a straight line because I'm going to be accelerating in both of those planes. And we would get some very different motion if we took those factors. But if we just have a constant velocity with a constant acceleration, we get this nice curved motion. So when this projectile goes, it's going to fly through the air, curving back towards the Earth until what happens? Until it hits the Earth, until it lands on the Earth. Now, what do you think would happen if it was thrown hard enough to miss the Earth? Now, what does that mean? Well, let's think of it this way. Let's think of a star football player who's going to throw a football off the top of a mountain. Well, when they throw it just so, well, that football doesn't make it very far before it lands on the Earth. So let's try throwing it a little harder, and it makes it pretty far, and then eventually it lands on the Earth. But we can see that as it's going further, there's more of a curvature on the Earth. What if we threw it even harder? What if we threw it so hard that it just missed the Earth? What do you think would happen to that ball? Just try stating your answer out loud. Well, what's going to happen to that ball is it would keep going tangentially to the Earth. You know what tangential means? It means in a straight line according to a circle. So it's going to keep pointing in a direction outward, but that acceleration is going to keep pulling it towards the center of the Earth. So at any point along this path, the acceleration is trying to pull it straight towards the center of the Earth, while the velocity is trying to go in a line that is, you could call this perpendicular to that acceleration, perpendicular to the center of the Earth. And so as it goes all the way around, it would keep getting pulled in by that acceleration. It would keep turning all the way around the Earth, forming this nice circular motion until it would smack that football player in the back of the head. So the variables involved in this type of motion, we would have a constant velocity and an acceleration. And if we have an acceleration, we must have a net force. And so when we deal with centripetal motion, we're going to deal with what we call a centripetal force. And this is going to be a placeholder force. So what are the components of a force? Well, first off, we're going to have a mass, right? Of course we're going to have a mass. It's a force. It's going to be dealing with a mass. And then we're going to have some amount of velocity, right? So we're going to have some velocity there. And then notice it mattered how hard I threw this, with what velocity I threw this. If my planet was bigger, do you think I would need to adjust the force that I threw that ball at? If it was smaller, you think it's easier to go around a smaller radius? Well, it is. And so we're going to have that as one of our factors as well. Our velocity here is going to end up being squared because we still need to have this all even out to the same units in a force. That would be meters per second squared times a kilogram, right? We need that on both sides of our equation. And so we can check our numbers here real quick. We can say that a mass, well, that's going to be in kilograms. Velocity, that would be meters per second, and it's squared, so it's meters squared over second squared. And then we have divided by a radius, so divided by another meter. That meter would cancel out that one, and we're left with kilogram meters per second squared. And so our units all line up, so this equation, we can say, rings true. So now, it's not every day that you go to the top of a mountain and throw a ball around the entire circumference of the Earth. So how about an example that kind of lines up with our daily lives a little more? Something that we could easily do at home. I've got a bucket of water here, and I can attach it to a string. I can hold that string in my hand, and I can spin it. I can give my bucket of water a force, a velocity, going to the right here. If I did that, well, it would have to curve upwards because of that string that it's attached to, and it would trace a circular motion. And if I'm spinning it fast enough, what happens to that water? That water ends up staying in that bucket. I encourage you to try this if you never have before. It's delightful. But that water is going to stay in that bucket. What is keeping the water in that bucket? Why doesn't it fall out of the bucket on top of our heads? And the reason for that is that it actually kind of is. As that bucket is midway through the air, we've got that water in there. What are the forces that are acting on that water? Well, the first force is the force of gravity. Force of gravity trying to pull this down. So is the water going to fall? Well, it is. The water is currently falling, but which direction is it falling? Remember, it had this velocity tracing it upwards. It had this force moving it upwards that was supplied by your arm. And so when it's at this top point right here, it wants to fall, but the sides of the bucket are pushing it to the left here. And so as that water falls, the bucket is actually moving into place in order to catch it. And so that water is falling, but the bucket is catching it as it falls. If we were to slow down as we hit the top, if we were to slow how quickly we're moving this bucket around in a circle, well, the bucket wouldn't be able to catch the water in time, and all the water would spill out. And if we sped up, well, we would just catch the water faster. And so that water is going to stay in that bucket if we move at a fast enough speed, at a fast enough velocity. And that velocity would be found using this equation. Centripetal force would equal the mass times the velocity squared divided by the radius of that arc. So when we talk about centripetal force, what we're really defining this as is it's not really a new force. It's not like the force of gravity or the force of friction, which are actual defined forces that we examined earlier. This centripetal force is really a placeholder. It's a way of saying, hey, what does the velocity here need to be to allow this thing to move in a uniform circle so that the water doesn't pour back out of the bucket. And so this force needs to be supplied. This centripetal force needs to be supplied by an actual force like the force of gravity. In the case of this water bucket, force of gravity would be that centripetal force. And so we could say, well, my centripetal force is equal to my force of gravity. So my mv squared over r would have to be equal to mg. My m's would cancel out, and I would have the 9.8 meters per second squared be equal to the velocity squared over r. And I would be able to determine values for that. I would be able to figure out where is that going to land. What radius do I need to have? What velocity do I need to have? And so that's what we mean by it being a placeholder force. Whenever we're trying to figure out that uniform circular motion, we'll need to identify what's the force holding us? Sometimes we'll have a force of tension, sometimes it'll be force of gravity. In satellite motion, which we'll examine near the end of this unit, we will be looking at universal gravitation as our placeholder force. So then lastly, we'll take a look at centripetal force versus centrifugal force. Centripetal force refers to the force that in that uniform circular motion is trying to pull that object in. But if you've ever been on like a merry-go-round at a playground and it's gotten spinning really fast and stood on that platform, stood in the middle of that circle, it feels like there's a force that's trying to pull you outwards. And so when we're on a spinning sphere or circle, we experience an imaginary force that seems like it's trying to pull us outwards. But that's actually our own inertia trying to resist the motion of this thing having a tangential velocity. So we see that, we feel that, and we call that a force, but we call that a centrifugal force because it is imaginary. It's not really a force that's pulling us outwards. There's actually a force trying to pull us inwards. And we have another force, usually the friction of our sneakers, that's trying to move the other direction. So when is a centrifugal force necessary? Well, this actually happens a lot in weather systems because as the Earth is spinning, the ground is spinning beneath the clouds, but from our perspective, the clouds are moving above us. And so it can be useful to imagine this in terms of a centrifugal force, even though what's actually happening is the Earth spinning beneath the clouds. We're not going to use centrifugal force, but it does come in handy in meteorology. We're going to be dealing exclusively with centripetal because this is physics. We're going to use real forces here. So in the next lesson, in the next video, we'll work through some practice problems and get to know how to use this equation a little better.